Functions and relations. A lot of this is review. Talking about relations, talking about determining if a relation is a function. We're going to look at two types of things today, and then tomorrow, or I guess for you guys Thursday, we're going to go through three objectives. So the first objective is to determine if a relation is a function. A relation is any set of ordered pairs. Okay. Whether it be an equation form or a list of different points, that's all that a relation is. So here is the official definition. It's on page 183 in your book, or you may take a picture of the screen. It's up to you. Any set of ordered pairs is a relation. The set of x values is known as the domain. The set of y values is known as the range. And we are going to find domain and range for all of these relations and functions today. And we'll do some more of that tomorrow as well. So here's the example that we're going to go through. This is also on page 183. So if you want to take a picture of this whole screen, or 184. Okay. So just real quick, this is the type of problem you're going to have to do. So they're going to give us a table like this. And you're going to first write it as a set of ordered pairs so that we can define the relation. Then you're going to write the domain in set notation, and then you're going to write the range in set notation. Now, the one thing that I'll tell you is that typically when you write a set of numbers, you put them in order from smallest to biggest. The book doesn't always do that, so I'm not going to get too hung up about that. Okay. But so take this table. Write a set of ordered pairs that you can come up with from this table first. Let's start there. So your set should contain 4 points. Okay, what's the first point? 3, -4. What's the second point? -2, 0. What's the third point? 5, 3, and then 1, 0. So this is what your set of points should look like. That's our relation in set notation. Okay, 3, -4, -2, 0, 5, 3, 1, 0. Then we have to write the domain, which is just a set of all the x's. So what are all the x's? Yeah, what are the numbers? I want you to tell me the numbers. That's right. 3, -2, 5, 1. So that's the domain. Feel free to put it in order from smallest to biggest if you wish. The book doesn't always do that. It would be my preference that you do it that way, so have it -2, 1, 3, 5. The other thing that we do with domain and range, we only write the values down one time, even if they show up multiple times. So when I write the range down, how many actual different values are there in the range? 3, because which one gets repeated? 0. So we only write 3 numbers down the range, -4, 0, and 3. We don't write 0 down again. There's no reason to repeat it if it's already in the set of those numbers. So that's how you write domain and range when you're given a set of ordered pairs, okay, or a set of points. You're not always going to be given a set of ordered pairs. Sometimes you're going to have an equation, and you're going to have a graph, and you're going to have to find the domain and range from your graph, and we're going to look at things like that tomorrow, or Thursday in your case, okay? Any questions about any of this? Should seem familiar. Okay? Let's keep moving. Determining if a relation is a function. Okay, a function is a special type of relation. Okay. All right. So the book's definition, when we have a relation in x and y, we say that y is a function of x. For each value of x in the domain, there's exactly one value in the range. I cleaned that up a little bit, and here's what you need to kind of think about. If an x value pairs up with more than one y, then the relation is not a function. So each x can only pair up with exactly one y. And that's what this part is saying here. So if there's an x that goes with 2 y's or 3 y's, then it's a perfectly fine relation. It's just not a function. Okay, each x can only go to one y, can only pair with one y. So on this next screen, there's 2 examples. You can take a picture of that. That's probably on page 184, 5, 6, somewhere in there. Okay. We're trying to decide. So let's look at this first one. Is there an x value that goes to more than one y? Does 8 go with anything but 4? Does 3 go with anything but -1? Does 5 go with anything but 4? No. Determining whether or not something's a function is all dependent on where the x goes. Even though in this case a range appears twice, it doesn't matter. Each x only goes with one y. So for this first case, this is a function. Each x pairs up with exactly one y. Okay. How about on B? Do I have any x's that pair up with more than one y? What one? -3. So -3 goes to 2, but then it also goes to 1. Okay, so this is not a function. And when you have a situation like that, your explanation has to be the counterexample. Okay? Meaning the illustration of what makes it not a function. Those are the things that you would write in each case. Is a function, is not a function. Okay? Questions? Right. There are other ways to determine if relations are functions, and we can look at the graph. You've looked at the vertical line test before. Okay. And the vertical line test is just a graphic way of seeing if there's an x that goes to more than one y. Okay. Essentially, how the vertical line test works, if you can draw a vertical line straight up and down anywhere in the graph that hits more than one point on the graph, then it's not a function. Because that means there are two x values that go, or there's an x value that goes with more than one y. Okay. If you can't draw a vertical line that ever hits more than one point, then it is a function. Here are 3 examples that we're going to try to determine if they are functions. Okay, so now take a picture and then we'll go through each one of those graphs and decide if they are or are not functions. So with this, all you have to do is draw one vertical line that hits more than one point. That's what you're trying to do. You're trying to find a place where you can hit more than one point. If you can't ever find that place, then it's going to be a function. So on this first one, a vertical line straight up and down. Is there ever a line that hits this blue graph more than once? Nope. I can't find a place to put a vertical line. And so drawing a bunch of vertical lines is no good. We only want to draw a vertical line if we can prove that it hits more than one point. In this case, that doesn't exist. Okay? So this is a function because there's no vertical line that you could ever draw that hits the graph more than once. Okay? How about the second one? Can you draw a vertical line that hits more than one point? Okay, so you have to make a little bit of an assumption because this kind of keeps going out. It doesn't ever straighten up. So this is the same thing. This is a function as well. How about that circle? Is that a function? No, there's a whole bunch of vertical lines I could draw that would hit more than one point. But all you got to do is draw one. So I drew one. And it hits more than one point. That means this is not a function. Okay, and so with the vertical line test, there's more explanation when it is a function than when it's not, because essentially my explanation is this vertical line. I demonstrated that it hit more than one point. So it's not a function. Okay. Questions on that? You guys have done that before, I think. Yeah? Alright, I think we're on to objective 2. And this is function notation. I know you've done this. Okay. Applying function notation. So we're talking about this kind of thing. Okay? So this function is called h of x. We can think of h of x like it was a y. But these values here, h of -3, h of 0, h of 3, what they're telling you is that's the input value. The input value in this case is x. So all you've got to do is plug those values in and simplify, and you'll be able to find h of -3 and h of 0 and h of 3. So why don't you go ahead and do those 3 problems, and then we've got 2 more to do after that and we'll be done. So on this first one, you're just plugging -3 in. How many got that? -15. Okay, good. Next one, plug 0 in. Simple enough, -3. And the last one, you're plugging 3 in. 4 times 3 is 12, minus 3 is 9. How many had all 3 of those right? Good. Last 2. And you'll see something like this. So sometimes you'll actually have other variables to input. Okay. So in this case, we have a different function. This function is f of x. The rule is a little different, -x squared plus 4x. Now I've got an input value that's another variable. And in this case, I have a binomial that's an input value. So why don't you try to work through those 2 things? This one is going to be a little trickier because there's a little bit more involved. This one actually should be really fairly simple. Whenever you see a single variable as an input, essentially all you're doing is changing the variables in the rule with it. So it's basically the same thing, except instead of putting x, you put t. All right? So it's just -t squared plus 4t. Just plug t in for x. B's a little trickier because I have to plug this whole a plus h in. Okay. And what do I need to do here? What does this really mean? I have this binomial squared. Yeah, you got to FOIL that out if you remember the rule. Okay, you got to FOIL that out. Don't make it a squared plus h squared because that's not what it is. Okay, when you FOIL that out, you should also have a middle term. And then you got to simplify from there. So when you FOIL that out, you should get a squared plus 2ah plus h squared. The shortcut for this is the first and last term squared. The middle term is multiplying by each other and then times 2. Then I distributed the 4, and then I have to distribute this minus. Okay, so that becomes minus a squared minus 2ah minus h squared, and then I still have my plus 4a and 4ah. There are no like terms, so that's it. I'm done. Okay, so these are the kinds of problems you're going to be working on today. Tomorrow we're going to expand it to more graphs and more domain and range from graphs, but that's what you got to work on today.